presentation somewhere in my life, but I will make better presentation and we can do this again.
This one yesterday or?
This is, yeah, put together kind of last night, yesterday,
Okay.
but, and not, it's more, it more will be lecture, discussion type. But, I'll try and go through so we can have understanding, okay? So this still isn't very well coordinated.
You can ask question, right?
Yes, okay. This is sort of like professor, not presentation. I mean, it would be best if I had big whiteboard, then I can almost draw a lecture, but this will work for now.
Okay, yes.
All right, so I'll also try and speak slow, okay? And please, anytime, ask questions, okay? All right. So my idea is I first want to talk about making a semiconductor and how a semiconductor works. And then from there, we will go into, okay, now today a semiconductor is very small. And then we will go into what it's like in the processing machine, okay? And how what we do connects to the processing, okay?
Okay.
So I'm gonna try and start kind of up here. And then go down to where we do. Okay. Okay. So,
Sorry,
yeah.
can you turn on your camera, please?
oh,
That's working already. You
okay,
can see us.
yes. So to start with, making a semiconductor is, think about making a cake, right? Only it will have more than 100 layers. And one layer is insulating, or one layer is conducting, one layer is insulating, one layer is conducting, one layer is insulating, okay? Over and over and over, all right? So conducting, think of like a copper wire, right? The copper is the conductor. And then we usually put a vinyl outside to it. That is the insulator, right? So the vinyl outside keeps, if you have two wires near each other, you don't have electricity go from one to the other, right? Does that make sense for everybody? Okay.
It will be separated.
Yes. So for semiconductor, because we're making them so small, we can't run a bunch of wires, right? So we actually have to make a conducting layer. And then we will paint or etch those kind of etch out the wire form in that conducting layer. Okay? And once that's done, we then lay down the next layer, which is the insulating layer. And we do the same thing then. We etch out the pattern for the insulating layer. Okay? Then next, so now we have some wires and we have an insulating layer. And now we're going to put down another conducting layer that we will make, etch more wires into. Okay? But think, we have conducting layer, insulator, conducting layer. We have to get the top conducting layer to connect to the bottom conducting layer, right? So after you put insulating layer and, form it, okay, then we have to drill little holes in places where we want the next conducting layer to connect to the bottom conducting layer, okay? So just think through over 100 times that process happens over and over, okay? And lay down the conducting layer, make the conducting line, which is now at the very base is only 20 atoms wide. And then as we get up, that wire gets thicker, okay? So I will kind of show that process, right? Does that make sense for everybody?
Can I ask a question?
Yes,
My laptop.
Yes.
I have Intel
the Evo,
i5
yes,
chip.
yes.
Is this over 100 layers?
It's probably about 70,
70.
yes.
Okay.
But then if you, in there, you have a NAND flash memory chip, it has almost 200 layers. Okay,
Okay.
and I have, if we have time, I can pull up, I'm going to show you a semiconductor circuit that is called planar, which is old type. It's like a town where everybody has one house, okay? NAND flash is like the 81-story tower in Saigon, right? It's bells up, okay? And now even your Evo, then, or your pinch,
How thick is this one? Is the Evo is this kind of thickness or what kind?
okay, so 70 layers is still, you can't even see the 70 layers. It's like, yeah,
Can I see?
can't see.
Okay.
They're literally like micron high, okay? So 70 micron.
So if I assembly this one, can I see the chip?
No, it'll be in a package. Then you have to take the package out. I'll kind of show you what the chip may look like, okay? So, but that's, so keep that in mind. It's at the top level, we're just making one layer, next layer, next layer. We do that many, many times, okay? And I'll come back to this, so we'll talk about kind of what Lam does, Applied does, and then what ASML. You hear the name ASML sometimes? That's the lithography. We will talk about that a little bit too. Okay?
ASML.
Yes. They're a little bit of our customer, not a lot. Is okay so far? Okay, so now, I'm sorry, online maybe I'll try this. Doesn't like it sometimes, but I'll try to do it this way. So, so I'll show a wafer in a minute, but this is an example of the base. That gray is essentially a conducting layer, okay? And then, so this is one layer and then putting on the next layer. So you put down, in this case, an insulating layer, okay? And the next thing we do is we create a pattern. Remember, now I have you think about, just like the cake, the layer goes everywhere across the wafer, okay? But I need to make the little wires, the little lines. So when you paint something, right, you put masking tape where you don't want the paint to go.
Yes.
Understand?
Yeah.
Okay. Almost the opposite for making semiconductor. We put masking where we want the wire to be. And where the masking is not, we actually etch out the material. So kind of opposite of painting. It's a little bit like if you masked your wall and where the tape isn't, you use sandpaper to sand away that paint, right? Then when you took off the mask, you would have paint remaining and no paint, okay? And where the paint is remaining is like the remaining conducting or insulating layer for that layer. Does that make sense? Okay? So you put down in the layer, just like, on a cake, boom, a layer there. Then we do our masking tape. Okay, now how we do the masking tape is, again, it's so small, you can't lay out the masking tape, right? So we put down a photosensitive, almost like a solvent, okay? It's like a thick solvent, okay? And it has a photosensitive aspect to it. So we put it on the wafer, so it's very uniform, right? You want it liquid, so just like if you spill water will spread out and be kind of flat across the whole table. Okay, so that's why we use more of a liquid or something that can be very flat. Because next we're going to have a mask over that area, and so that mask will be the pattern you want to make, this pattern, okay? And then what happens is, so that the the wafer with the layer and the photo stuff is here, the mask is up here. We actually then flash light, okay? It goes through the mask and it exposes where where the light goes through, it activates that area in the masking material, okay? So once we've done that, we go over and now where that's exposed, it essentially binds that area. So then we put it in a solvent and we remove the masking material where it wasn't exposed to light, okay? So now it's just like when you put tape on your wall. Now when that comes out, I have areas that are like tape. Okay? All right. So that's this process. Then we come to like a lamb tool. Okay? And now you have, in this case, you have your conducting layer and you have your mask, you have your essentially the open areas, right? So if you remember, I'm not going to paint, I'm going to sand away this blue material, okay? So it goes into a lamb machine or an AMAT machine. And what it does is, again, so very small, so there's not a physical way to do it. We actually, let's say if this is, a conducting or an insulating layer, which is, let's just say this is an insulating layer. Insulator is typically silicon dioxide, basically glass, okay? Silicon and two oxides, okay? So in the lamb tool, we will flow in to our gas lines we make, okay? We will flow in fluorinated gases. So we will like carbon tetrafluoride, 1 carbon, 4 fluorides, or we call it dihexafluoride, dicarbon hexafluoride, which is 2 carbons and 6 fluorides, or a sulfur hexafluoride, which is 1 sulfur atom and 6 fluorides, okay? So we will flow those kind of gases in, okay? And then once they're in there, so just for right now, think of the wafer sitting in this chamber and these gases are all around it, okay? Then what the lamb tool does is it puts an electric energy into that gas ball, okay? And you get a plasma, okay? So if you remember neon lights, right now we have the yellow, right? If you remember a neon light, so that's actually the gas neon. And when you put electric voltage to it, it actually ionizes it, turns into a plasma, okay? Yeah. And the light is a photon. When an electron excites and moves to the next level in an atom, it ejects a photon. So that's how you get neon light, that you're seeing the photon from the planet. I get a little chemical, but so you can relate to a neon light. So when I applied that charge, like I mentioned earlier, I had a carbon and CF4, carbon with 4 fluorine atoms. I mean, and they're all binded together. The electricity allows them to break apart. So now I have a carbon atom floating around and maybe, an F2, 2 fluorines together and a single fluorine by itself, okay? And so I create this gas with a lot of carbons and fluorines floating around, okay? Can you see that? Yeah. So then, I mentioned earlier, this is silicon dioxide, okay? So silicon reacts with free fluorine. So as these areas are open, are exposed to this active gas, and they're excited, they have some energy from the electricity. They come down and then even though the silicon and the oxide are sitting combined together, the silicon says, hey, that fluorine kind of cool. It's all active and dancing around, and it gets pulled, chemically it gets pulled to the fluorine. So basically 4 fluorines gather around and pull away the silicon from the oxide. So now you have what's called silicon tetrafluoride, okay? And now you have an oxygen atom floating around, right? Well, what is oxygen like? It likes the carbon. Remember, I have carbon floating around. So the oxygen combines with the carbon, the silicon's all happily dancing with the fluorine, and now they're both gas phase, and they get pumped out of the chamber as a byproduct, okay? And that's to relate to what we do. Sometimes you see we do the bigger 4-inch LOD stuff. That's typically after the chamber that's taking away the silicon tetrafluoride and stuff, okay? So that process is just happening where you're just eating away with your fluorines and carbons, the silicons and the carbon and the oxygens are happily dancing away with their new partners. That makes sense?
I don't really understand fully, but I know that the machine, lab machine is in that process.
Yeah, lab machine is in this process, yes.
How about the others?
Okay. So now that I've removed my silicon dioxide where I want, okay, I have to remove this mask. Okay, so then I come to photoresist removal. And yes, Lam has another machine that takes just this away, but doesn't affect this. So again, you have to then, all this is about chemistry and energy. So this is a certain material and it'll react with other, so this is a material that reacts with oxygen, okay? So then here, I make just a highly oxygen environment that kind of effectively just almost like burns away this material, okay? But silicon dioxide, when it sees another oxygen, doesn't care. It doesn't get excited and wants to go join that oxygen. You see what I'm saying? If I put fluorine to take this off, then I'd etch away this stuff. Am I going way too fast?
To last year,
It'll hopefully come together a little bit, but I want you to understand that what Lam and Applied do is really a gas chemical mix that we put a wafer into to either etch away or push the film down. Okay? So now, once I've cleaned it all off, and you notice how we talk about residue and particles, right? So then it has to go through a clean cycle. So if our gas line had little bits of free metal in it and those come out and are on here, they need to get cleaned off or they can cause a problem, okay? So then, now that I have this done, I need to put my next layer of cake on, okay? So in this case, I put down my conducting layer, which notice how, remember I talked about once you put down the insulating layer, I've got to make a bunch of little holes for the conducting layer? Yeah, so these are the holes. This is a conducting layer. It's hard to tell, but this is essentially then a line, like a metal wire underneath. Now I'm going to start this process all over again to make the next layer of wires up here.
100 times.
100 times.
Yeah.
Over and over and over. Are you guys with me? Okay?
50%.
Huh?
50%. It's right.
I actually, very short time to make this, but hopefully this is first thing, and I will make the whole, I'll find, I used to train this a little bit, so.
I understand that process because you can both onto like a
Yes.
somebody.
I can see your.
Answer me.
Yes, he knows this, yes,
Go
yes.
onto like that.
So answer me, do what? What is the product?
The chip.
The chip?
Yeah.
Similar to Intel.
Yes, the different chips, but yes.
Can you see the chip in answer me?
Yes.
How small?
Yeah, very small.
Yeah. Some of them like, so, I have a big fingernail, but an Intel chip now would be both my thumbs. Yeah, yeah. Some of them are very small, little geeky chips, right? For doing certain things. So now, you hear us talk about wafers. So we start with a silicon wafer that looks like the one over here. Okay, that's just a bare silicon wafer. Okay, and then when we build up those 100 layers, you can see on this one for people online, you can see the little square areas. Those are each a semiconductor die. Okay, so like I said, you can see how 100 layers, it doesn't really make much most of the thickness is still the wafer itself. Okay. And so afterwards, then that along those lines, those are called stride lines, they cut the chips up and they put them into individual packages. Okay, so just think, we start with that wafer. And that wafer is essentially a conducting layer. Okay, that's what we use it for. Okay. I'll come back to it. Remember, it's called a semiconductor, which means silicon. Silicon can either conduct or it can be an insulator. Right. So they start when we start the wafer, we actually do some early processing to make some areas conducting and some areas insulating. Okay. All right. Now. Okay, so this is how a semiconductor works. Okay. So at the very bottom of these 100 layers in an old style semiconductor, like your Intel chip, okay, is this is a planar, so like one house in a town, semiconductor. Okay. So what you have, I'm gonna have to stand over here and just do it. Okay. So this is the silicon wafer. Okay. And remember I talked about we put certain we treat the silicon wafer to make some areas conducting, okay, more than others. So we create two areas for electrons to come in here. And then when we turn on the switch, the electrons flow over and out here. So we wind up with a circuit, just like this light switch. If I boom, semiconductor off, boom, semiconductor on. Okay, that's all this is. This is a light switch. Yes, it's just you can't stick your finger in there and turn on 2 billion transistors at a time, right? Okay, so what we do. This area is treated with certain little particles, chemistry, okay, to make them conductive, okay? This area is made essentially to be either conductive or not conductive, all right? And it's structured such that when this is turned off, basically a positive charge that moves up into this channel and the electrons can't flow through, okay? When we turn on, or just like when I flip that switch, when we put a voltage to this electrode, it forces the positive charge down and the electrons go, yay, I get to go across and they go over here. That's how it turns on and off, okay? That's okay. So now, in this picture, this is right here. Okay, and then this is the little switch. This area, all this area around the gate, which would be up here, is that next insulating layer. Okay, this, if you remember, we at the end of that last photo, we put down, we put down the next conducting layer.
The orange color.
Yes, the orange color one. That's this layer. So this is where, in a sense, what you don't see here, but this is the wire that comes down here to supply the electrons. And this is where the wire goes back out to the ground. Okay. So think of just like in this building, this light switch has a wire that goes all the way out to the power outside, right? In reality, somehow it makes it all, because the electrons come from there to this light switch. You turn it on and you have lights. Okay. And then the electrons go through the light and they go out to a ground, right? And so somewhere in this building is a ground. So just like that, and there's many rooms that have to have all the different wires going to it. So each time you have to build, they come up and we have to etch or create the pattern and make many different wires that go to the different, the different switches, just like the different rooms. Okay? And what what has to happen is, because there are so many switches, you know, if you think about a trend, like your Pentium today, what do they say? There's 2 billion transistors, okay? So think if we had 2 billion light switches in here, okay? We probably have stacks and stacks of wires and, you know, to run, okay, this group of wires goes over to that set of light switches, this group of wires has to go over there. So an Intel one, if I go to the next, I'm going to really get confusing here. This is hard to see, but this would be like an Intel chip. So that transistor is down here. It's not even on this photo. And then this is 8 levels of wires that, just like here, we had 2 billion transistors. You have these big wire cables just stacked on top of each other to distribute across all the transistors. Okay, but the real working of the chip is down here. The rest of this is all just to connect them out to the world, so we can see it on our computer and we can tell what to do. Okay, okay. So sorry, but
50%.
yes. Okay. So that's kind of how we start with a very simple concept, layer cake. Okay. In simple concept, masking, and remove away the paint where you don't want it. Okay. But as we made chips smaller and smaller, we had to figure out how to do it in a chemical way. Okay. Right. So then we come to, these are applied material processing equipment. Okay. I'm trying to use this one. This is a little better. So remember those wafers I showed? Remember the wafers?
The orange color.
Yeah.
The rounded.
The rounded, right? So yes. We go back here.
Yeah, that one.
That one? Okay, in fact, this is kind of sitting near a little robot area, you know, or this one. So these are now 300 millimeter in diameter.
300.
Okay?
Yes.
Yes. A little bigger, I think. Yeah. Okay, now. Okay, so those wafers the wafers are sitting in here. Okay? This is basically out like in here, in atmosphere. Okay? We can't process at that very fine level in atmosphere. There's nitrogen and other gases and particles out here. So remember, if I have like a very pure silicon dioxide film, and I want only fluorine and carbon to help me etch it, if I have air involved or I have nitrogen, the nitrogen is going to chemically react and I'll wind up with nitrogen in my transistor and it won't work for them. Okay, so that's why we have to do semiconductor processing in a very deep vacuum. So we take the wafer from here. All this is just robotics to move into these chambers. Okay. Okay. So the wafers go in and this is now would be in vacuum, it's called. Okay. So this would be kind of equal to the vacuum at maybe 60,000 feet in the air here. So you're in the early part of space. Okay. This is typically about, maybe it's about 10 to the minus 9 4. Okay. Okay. Then, so once you get this all set, the wafers go into this processing chamber, which again will start in the like kind of deeper vacuum 10 to the minus 4. Once the wafer's in there, we start to flow our gases. Okay. And unfortunately, it's all covered up, so you can't really see it. This shows a little bit. We start to flow our gases. And then once the gases are flowing, you kind of see these wires going to this. This is, the wafer would be under here. We apply electricity. And that electricity makes those gases get excited. Remember, now the fluorines and chlorines or carbons are dancing around. And the silicon dioxide says, oh, I want to go party with those guys, right? So that's kind of what happens, right? So we run that process for a while. And then when it's done, the wafer will come back out, go out here.
a new wafer goes in, and they do that over and over and over for about 50 wafers at a time. So like, if you remember that first one where we etched the holes, okay? So that would happen to all these wafers. Then they would go to another machine that would clean off that mask. Then they would come out and they would go to another machine that would do all the super clean, it's kind of a wet machine. Then they come back out and then they go to the one that puts down that orange layer, okay? They all kind of look like these machines, but the process chamber here does something different, okay? Okay? Understand? A little bit?
Yes.
Okay. Then,
That dish for machine here.
yes,
The dish will go 100 times.
this machine, yes,
The dish,
the wafer.
the
Yes.
wafer.
The wafer will go, so the wafer, to do this layer, the wafer will go, yes. So let's say for just this layer, okay, we're doing one layer at a time. It will go into here
Circle.
one time,
One time is one layer.
one layer.
Okay.
It'll come out, but remember, that was just, in this case, that was a step to etch those holes, okay? Now it needs to go to the next step to clean off the mask. That's another machine like this. Okay, and then it'll go to another machine to make sure we clean off any particles. Then it'll go to another, they all kind of look like this, then it goes to another machine set that does the next layer, okay? Then after it gets its the masking tape all on it, then those wafers come back, now they're at layer 2, they come right back to this machine and start to do the same thing. Okay, so over 100
By
times.
robot.
Yes, robot, right, so these are actually called front open something pods, okay? There's overhead robotics, so these actually, almost like a crane over a shipping boat. They come and pick these up and take them over to the next machine, okay? All right. So what we do is we make gas lines that deliver all the gases into this chamber, okay? And underneath, it's hard to see, but there's like a vacuum pump here and stuff. We make all the lines that then take the happy little, silicons that are combined with the fluorines and stuff, and they dance on out through our 4 lines out to the gas pad where they're cleaned up. Okay, so that's what you'll be doing here, is making gas lines for here and the 4 lines that take away the material. Okay, I couldn't find a good picture for that. I'll see what I can.
Where is this one?
So this one's our,
We need the.
this one would be, it would either be under here somewhere or up here. So this is an argon, so this is not a critical process gas. That's probably why this is a looser term. It would probably be somewhere under the middle here because you'd have argon coming in and it would be sending it out to the gas boxes. Like look at this, there's 1, 2, 3, 4. So this is probably, AMAT has there might be a chamber over here. This is probably a 5-chamber system. You got, where's the argon come in on this one? Here, this is where the argon comes in. Okay, and then this was sitting here. The one argon's going to that chamber over there. One argon's coming to this chamber. So you could probably turn like that because there's a chamber back here. And then there's an argon going to a back chamber, and you see what I'm saying?
Okay.
Okay, can you kind of envision that?
So that one is to connect that machine to
There's a
other
main,
machine.
no, there will be a main argon line coming into this machine to deliver argon gas just to this machine. One line coming in.
Yeah.
And then I've got all these chambers to one argon. So the argon comes in on this line. And then it goes out to that machine,
To that chamber.
to this chamber, okay?
Okay, so they connected.
Yes. Okay,
So you did machine.
this one is an AMAT machine, the land produced similar machine, yes,
Yeah, big machine.
yeah,
And machine the component of that machine.
exactly, correct. Okay. So I'm trying to say one more thing and then we're gonna go next. If you go back even 10 years ago, a machine like this probably had 2, maybe 3 process chambers max. okay? And the reason, and now, like Lamb's newest machine, which is called the Sensei, has 10 chambers, okay? Every one of those chambers needs 6 gas lines, okay? So the old days, one machine had 2 chambers, 12 gas lines. Now, one machine, 60 gas lines, okay?
Yeah.
I don't even think Lamb understood the exponential growth that meant. So their toughest area is weldments. They cannot get enough weldments. Okay. Why so many more chambers? It seems counterintuitive, but as we have gone to, so not only are the transistors smaller, the film thickness is down to molecule level now, right? They have atomic layer deposition, so it's actually atom level. It's so precise, it has to be a slow process. So in order to get production, they need more chambers. Okay. When films were thicker, we removed basically tons of molecules at a time, billions of molecules, right? Now we deal with one layer at a time.
Yeah.
Okay.
More precise,
Yes.
need more chambers,
Need more chambers.
need more.
Need more gas lines. Happy for us. Okay.
More work,
Yes. Okay.
more order.
So this is kind of blurry, but this is looking into like a gas box for one of these machines I showed. So you can see 1, 2, 3, 4, 5, 6, 7, 8.
So the valve,
Yeah, that's 8 valves. Those are neutral valves, right? So 8 gas lines for this, and then you've got also different shut-off lines and mass flow controllers, okay? This is then kind of this type of box, but this is what this is a 1, 2, 3, 4, 5, 6 gas line box. Okay, 5. 1, 2, 3. So those 1, 2, 3, 4, 5. You're right. Okay. So, and you see, you guys recognize this stuff, right? Okay. So you got to bring the gas in. You've got to go through a valve, get turned on, then we do some of these fittings, right? So we do a lot of this stuff. Okay. Our next phase, I don't know if you've heard Drury, the Lamb guy from Korea, right, mentioned someday MDC will do gas lines. Okay. So our next step is to do the whole gas line.
I didn't hear that.
Oh, I did. That's actually where the big money is making the whole gas lines. Okay. So you can see exactly now, you're starting to see our product, right? So you go back here. Here's the machine, one layer. Somewhere in this machine is that gas box with our 6 or 7, gas lines. We have all those gas lines going, all those gases come into this machine area. And so we're making lines to bring the gas to the gas box. And then we're making the lines that go from the gas box up into this chamber. Okay? So that's what we do, right?
Can I ask a question?
Yes.
This one is the qualification part, so bring here.
Right.
Is this one inside that
This-
chamber
No, this would be probably below the chamber.
below?
Yeah, that's a bigger part. So that one is usually then, like I said, after the silicon and the oxygens combined with their new partners, they go down that line out to the outside the fab is called the scrubber, and the gases go through the scrubber, and it's like rain, so it just cleans the gases out.
So this one is to throw away the one
Yes.
we need.
So that one would probably be somewhere underneath here. Okay. And then you have this is a turbo pump. So this pump is pulling down this to vacuum. Okay. And then there's a line from this turbo pump that actually goes all the way down below this floor. So in a fab, there's a whole nother basement where the main pump areas are. And so this is the pump that takes it down to super high vacuum, but then that pump is being pulled by another pump down in the basement. So all that line we do. Okay.
Are we able to say that this one requires more quality than this one?
Yes. That's why that's usually outside hand weld.
Yeah, yeah.
This one's cleaner.
Okay.
This one we call, you remember we call this one UHP, ultra high purity.
Okay.
Right? Because that's anything before the wafer, UHP.
Yeah.
After the wafer, typically LOB. Okay, this one typically, it's EP, those type of things, those usually, they may or may not need it. If they do electropolish or something, what they're doing is trying to make the surface as smooth as possible. So what happens is when you have fluorine and it combines, especially sometimes, so I said fluorine, yes, fluorine will combine with silicon, right? Okay, but in that dance, there's still some carbon fluorines together, okay? You know when you have a frying pan and it has Teflon on it, right? So it's non-stick? You know what I mean?
Can I stick on the Teflon?
Yeah, right. So, you know what Teflon is, right? Like a frying pan that has a coating so that nothing sticks to it. You know what I mean?
The white color?
Yes.
Similar to
Yeah.
plastic?
Yes,
Very hard?
very hard. That's actually a carbon fluorine monomer chain, okay? So part of the process that's going down outside the chamber are things we don't necessarily want, but they're still there, which are like carbon fluorines that are still together. As they go down and they find a piece of this gas pipe, they stick to it. And over time, we build up basically a Teflon layer, okay? And it gets thicker and thicker and it starts to flake off and causes particles. That's kind of not important, but you start to understand why we sometimes try and get high, high layers or high. Okay, so this now is, think of, now I'm showing you inside the chamber. Okay, this is a drawing I did. Okay. This is a wafer, this gray zone, and there's all the mat. This thing's ready to get etched. Okay.
Okay. That's the orange dish.
Yes.
300.
This is a 300 millimeter wafer. Okay. It sits on a pedestal. Okay. And this pedestal is usually can have power to it. It's usually grounded as well. Okay. You can see up here. Here's something that looks like our gas line. Okay. So here, just think if there's 6 gases coming to this chamber, there's 6 of these lines coming to this, okay? Then the gases kind of flow in and then they flow through a shower head. So they kind of disperse all up here and they come down just like in, your shower in your bathroom, right? There's just water pipe that comes in. So if you didn't have a shower head, it just hits you with water, right? But because you have a shower head, it kind of sprays out all over even, okay? So that's what this does, okay? So now, here's the gas happily coming through an MDC line, comes down here, and you can see, so the gas is flowing all kind of evenly across this whole thing, okay? That seems simple, it's not simple. I mean, getting even gas flow, very difficult, okay? Now, once I have the gas all happily flowing, I apply a charge up here. Okay, so this is hooked to, this is hooked out here to a generator. The generator turns on, this now has an electric charge to it. This is grounded, so you wind up with an electric circuit. In between is the gas. The gas gets excited, so now the fluorine breaks away from the carbon and is out here dancing around, and the silicon dioxide sees the fluorine dancing around, and it says, I'm going to go play with the fluorine. It grabs the fluorine, and then it gets pumped out down into the basement. Okay?
Okay, that 2-inch is below.
Is below here, yes. Okay, how am I doing? Okay, so so are you guys kind of, does this make sense a little bit? Okay. So now when you get into, this is what I did. I was a plasma physicist. Okay, I was a geologist, but then I learned this on the side. So this gas flow, just think about this. This is 300 millimeters across here. Okay. I'm across this wafer then is 72, if you do the math, there's 72 billion transistors I'm making on one diameter line across them. One diameter. Think about it, remember this is a circular wafer. So think about how many diamond lines you have, right? So in other words, there's gazillions of transistors on this whole wafer, okay? Each transistor in today is 20 molecules wide,
Really what?
20 molecules.
Okay.
Excuse me, no, sorry, 20 atoms. Yeah, sorry, 20 atoms wide, okay? 72 billion of these, 20 atoms wide, okay? If one of these areas, the gas flow is not quite right, so now there's a silicon dioxide that just says, you know what, I don't want to deal with that fluorine guy out there, okay? So he stays. Now I'm 1/20th, okay? I'm 5% error versus the next one. And the transistor doesn't work, okay? So, you know, we feed the chamber kind of like this. If we have a weld imperfection out here or contamination out here versus this side, more gas will flow to this side because it's less restricted. You'll have an imbalance in here. And now this side, the transistors will be different than this side. That's how important it is, okay?
So the penetration of the weld is
Important, yes. That's why vacuum welds, you know, we can kind of do the weld from this out, but it has to be very smooth in there. That's why Samant trusts Best Test. Because that's what he's looking for. Is our weld smooth? Is it concave? Is it convex on the inside? Is it porous? Not porous? If it's a porous weld, it's absorbing some of that gas. Okay? So that's why all that's, it seems simple. You look at this and okay, easy to, you know, but it's not. But that's how we are so important to making your Pentium run. All right, so I'll shut up for a second. Questions or? Kind of talk fast, I think. Yeah.
I have a question. We refer concave or concave well.
What would be the problem with it?
What style of which is
You actually wanted the weld on the inside of the tube to almost be as not concave or convex, just about as flat as you can. Yeah.
flat and then diameter is the same width.
Yes. Yeah.
Always tubing. The more flat, the better,
Yes.
right? Make 100% flat.
So that's how, simple concept, layer cake, right? Simple concept, okay? You know, the way to make a lot of them is just on a wafer. And then, you know, of course, this is just how the design works. But then in the end, it comes down to, you know, going back, you know, doing the layers. You know, remember, like I said, there's a layer where we etch, then it'll go into another machine that kind of does the same thing, but it has different chemistry, a little different setup, and it does the takes off the mask. Then it goes to another machine to clean, then it goes to another machine that deposits the conducting layer. So when you hear laminate apply, we'll talk about etching and deposition. Okay, those are the two areas they're the best at. Okay, and they're, you know, so, and we do gas lines for both of their most advanced etching and deposition. And then they call their etcher now ALE, atomic layer etching, and ALD, atomic layer deposition. Okay, where they're really doing one atom layer at a time. So that's kind of the simple what's happening to me. I'll make a more complete, but also, so the next thing, so first I'll shut up. Are you guys?
Yeah, more questions.
Yeah, more questions or thoughts?
I have one.
Yes.
At the beginning of the laptop,
Yes.
how big is the chip?
Wish I had myself. So, like, for example, I worked on 8088 chip, 8186, 8286, 8386, up to the first Pentium. So I was in Intel for that time, okay?
Maybe this size?
No, so an 88 chip was probably in the package was about the size of this can.
That's small.
That small, yeah, okay. The,
Before that?
before that even smaller, so the 8088 was really the first, like in the first IBM PC was an 8088, okay? Intel's first logic chip was the 4004. Okay, that was the first processor. It was probably like what you were saying, would be probably half my little fingernail. Okay, very small, okay? I have ugly fingers, so sorry. The 286 was about the size of my thumbnail, okay? The 386 was, about 1.5 times bigger than my thumbnail, okay? So, the 386 was the first microprocessor that could do multitasking. So you know how today you don't think about, you're running Excel and you switch over and you run Word, okay? Before the 386, you had to close Excel.
Open Word.
And open, yeah, and boot Word. I mean, so you literally, and before hard drives, you'd have to close Excel, back then it was Lotus 1, 2, 3, pull out the floppy disk that drove that, put in the floppy disk for, it was Word Perfect back then, and then you'd have to boot it up. It takes forever. So, you take for granted all we can do now, but that's what we do. Does that help a little bit?
Yeah.
Okay.
You made this line,
Yeah, I made that one.
copy and paste all the arrows?
Yes.
Okay.
Eric Schwartz laughed at me, but it kind of gets the concept across, right? Yeah, I made that slide. I don't sleep. This is sometimes it's like, okay, I'll do this kind of stuff. Because I wanted to show, what we do. Sometimes I use this for investment people and stuff like that too. But, so
I have this product, the one with the hose.
yeah,
Is that inside the chamber just now?
no, that would probably be something for like nitrogen to drive like a valve open and close or something like that. I doubt the hose would be on any gas line to feed into the chamber.
If so, I guess the requirement of this is not critical than this.
Yes,
This one
correct.
is more.
This would be more critical, yes. Let me just,
Inside 14, our qualification part, only this one require hydro test.
yeah. This first. Okay, if you guys want to have a little more fun, and maybe don't. So I don't want to do it. Never mind. I can show you how the new transistors are going to be once we got to this.
Next question. How
Yeah.
strictly is the bellows in this 2-inch? The design, the corrugation need
Yeah.
to be 100%.
No,
Oh, we
usually
can-
the bellows, there's some level of tolerance, right? We buy the bellows outside.
Can we buy a similar design? A similar design to what we are buying
Yeah,
from Ameriflex?
sort of. So what they worry about more is there is some relationship to, yeah, you want a certain amount of, you can't deviate too much from the, kind of the, what do you want to call it, but the shape, okay? And the metal thickness,
Yeah.
because
Affect to the flexibility.
it affects the flexibility, it affects how much of, remember I said some of this stuff goes down the evacuation line, it deposits. So you can have like, chlorine gases that'll deposit in, so the deeper that fold, the more you might get deposits. That's corrosive over time, especially if the bellows is too thin, it'll corrode out and now you have vacuum leak and
Okay.
stuff like that, so,
The reason I asked is that me and one few days ago.
Yes.
We met one fellow supplier.
in, where do they make the bellows, in Vietnam?
They buy and sell. But he said that I will not buy and sell for this one. I will introduce you someone else in, around here, Asia.
Okay,
But
yeah,
But the dimension, the thickness will be a bit different.
yes,
So can we propose to lump?
you can do that, so the engineering, so if we do that now with some bellows and stuff too, so yes.
Okay,
I think in fact, that's the idea, I think Declan and Trevor have for you guys, is to find those,
okay,
then, because Lamb also wants to support a local supply chain.
okay,
So we'll have to go through qualification of it.
okay. We get the samples, send to them.
Yeah.
If okay, then we can buy.
Yes. You,
1 hour already.
okay, so we're done.
Any more questions?
Regarding this, we do in outside.
Yes.
For outdoor diameter only.
Right.
Without inside.
So EP outside is generally for visual.
Yeah.
Right, so customers pay, what, $10 million now for a Lamb etcher? That comes in all scratched and ugly, they then go, what are you doing, right? It's crap, so it's more just visual, yeah. But the inside is critical for gas flow, okay? And then sometimes you guys will hear the topic VIN bar or VIN dim or double melt, okay? So that is material that, you know, start to make the steel, you melt it down, okay? Then, you know, you make the ingot. And that still has a certain amount of oxygen and impurities in it. So you do a second melt, usually VIN means it's a vacuum melt. They melt it again and it's under, you know, believe you have this molten steel under vacuum. So now oxygen and impurities are bubbling off and being pulled away by the vacuum. And then you let that cool in and now you have a more pure steel. And so for their very advanced stuff, they sometimes ask for, you know, usually it's called VIN bar or they just say double melt. And it's on lead time, it's a pain. But that's what they want it for. They have even higher impurity needs. Okay.
One more people.
Yes, on the outside. Yeah.
Pretty sure.
And that's why too, when, as the team grows here, it will give it pressure to move things, scratches, just weld imperfections, all those kind of things, customers reject all the time. So, you know, that's why, again, polishing seems simple and grinding is key, right? Because otherwise, you know, fabricating metal, you're all gonna scratch it, you're gonna do some things. Polishing and stuff helps keep it, so it's a, you know, not a good surface pre-weld, but afterwards to make it look good. Okay. So my, running out, I can go on and on.
One more product for the PDP product.
Yes,
PDP
yeah,
PPD product.
Yeah.
Just now we talk about the application of the GDP product.
Yes.
Here how about the VDP product?
yes.
Has all the good questions.
The valve? Yes.
What's the application?
Let me go back to here. We saw this going on, okay? We're not the best. Any valves? Okay, maybe a little hard to see. You can see this line coming off here, okay? This is actually a valve. Okay, this is one of our gate, not ours probably, but a gate valve, okay? An angle valve is like
this turbo pump has a pipe coming off of it, okay, that's gonna go down to the subfab, okay? Between the subfab and that is going to be an angle valve, okay? So, and mainly because when the valve's open, you're pulling stuff down to the subfab. If you want to work on the subfab or work on this machine here, you close that valve, okay? And so this is the valve body.
Yes.
Okay, and then in here is just something that opens, you know, it's always hard to describe, but it's a flat plate with an O-ring. And then there's a pneumatic actuator, pulls it up, then vacuum flows in here, and down here. Push down, and this heats down in the bottom here. Now, this goes to the chamber, that goes to the pump, they're now isolated from each other, okay? So another thing, like, you know how we do leak check, right? So this machine has to be leak tight, okay? And so every time they touch it or work on it, they have to do, first thing they do is they do what's called rate of rise. So they pump it down and then they close every valve, okay? So if it's leak tight, the pressure won't move, okay? But if it's not leak tight, slowly over time, the pressure goes up. So then they know I have a leak. So that, you know, valves are used for that too, where they isolate the whole machine. Okay. Now, once it's leaking, just like we do leak check, you know, so where I learned the leak check was fixing those machines. Okay. I mean, you gotta leak check that whole machine. And it could take you days.
Roughly, what is the working pressure of the valve?
So think about, okay, so
I'm asking that one because I see this one is too thick.
Yes.
No need this thick.
it's not. Yeah, probably that's an overkill for thickness. Some people use there's some levels, so that you have atmosphere out here, okay?
This is negative.
Yeah,
Pressure,
vacuum,
right?
yeah, right. And so probably the thickness just helps you think about that pressure. If you close this on this side, which is down to the pump, you get down to, again, high vacuum, 10 to the -9, okay? And if I vent my chamber, I have atmosphere coming in on this side, above the valve, right?
Yeah.
So the pressure difference is atmosphere down to the vacuum at times.
And can we say how many bar? 1, 2, 3.
So what's atmosphere? 764, 1 bar. So this atmosphere, you have 1 bar here. Probably, so then, like I said, I think in torr, not bar, sorry, this is a metric to.
Bar.
They're making me do the converter, that's a converter, okay. Let's see if this will work. From 10 to the -9. Let me convert. I had a valid number. Point 1, 2, 3, 4, 5, 6, 7, 8, 9, 1. Okay, 1 times 1 to the -13 bar. To 1 bar on one side to 0.00000000001 bar.
So is that
That's
below
space.
or above 1 bar?
Is that below 1 bar?
Below, but very little, correct?
Yeah, very little.
Yes.
So
Okay.
think about the pressure difference,
Okay.
right?
Different, very little.
Yes.
Yes. How about the pressure of this? The similar to that one?
So when this is flowing, so this will have some pressure, maybe slightly above atmosphere, but probably about atmosphere inside flowing. And it'll be going into a chamber that will be,
So I think in this industry, pressure is not.
so this will be going into a chamber that is at 0.00001 bar,
Okay.
okay?
Below 1, very
Yes,
little.
very little.
Okay.
And then
again, it's that's in the process chamber. Then as you get down towards the pump, it's getting down into that -13, okay?
The reason I ask is that I work for, piping.
Right, that's right.
On rig, the
Yes.
pressure is important,
Exactly, yeah.
but our product is not.
It's not, I mean, this
As
stuff
long
is kind of
as-
over-engineered, so you don't worry about that
Yeah.
pressure differential as
Okay.
much, okay? We worry more about, so we kind of over-designed to take that out of the equation because we have to worry about, you know, again, the purity,
Yeah, goodness.
the cleanliness, the smoothness, okay? And the other one is so vacuum principle, right? So everything we do, when we make it like a vacuum chamber, you want kind of, just like this, you want more, as much as you can, in where the vacuum is, rounded surfaces. You know, where you have sharp surfaces, you can trap particles, or you can trap small molecules of oxygen or something that is difficult to get out gas for a while. You want, you know, that's why the welds can't be porous. You don't want what are called like dead ends, right? So if you have to, you know, like technically, these don't get vacuumed, but these are dead ends. These are, you know, tapped holes that go down in, okay? If I then put a bolt in here, there's air trapped in here, okay?
Yes.
And then if this, and if it technically, let's say this was the floor of a vacuum chamber, that little air could leak out for 2 weeks. Okay, and then, you know, I do my leak rate test and I keep failing and failing and I keep doing leak checks and they're not, they're not. So then you hear people talk about vintage screws where I'll put, the screw has a little hole in it so that the air pulls out right away. But my point is, when we design these things, we design with all that in mind so that we do not create bad vacuum areas.
Yeah.
Okay, that's a whole other class. Actually, we're trying to get an outside set of videos and stuff for that, so you guys can learn that. But I'm talking way too fast, aren't I? Is it okay? Sorry.
It's okay with us.
Did this help
Yes.
a little bit? Okay.
One more question? Do you have any? No more. I go to the next.
Sir, I see that this product, PPD product and DDP product used in the same machine or plant. Why do we divide into the two types?
Good question. So vacuum products, VPD. It's not only valves, right? There's flanges, so that it's used on vacuum systems, okay? Valves, flanges, you know, reducers, nipples, all that stuff, okay? This is related, but it's specific, it's more specific. So this is more about the vacuum system, okay? Building the system with a pump so I can take it from atmosphere to vacuum, okay? That's the valves intend for that. The flanges are all about creating a tight environment where I can have atmosphere on the outside and deep vacuum on the inside, okay? And no leaks, so I don't get impurities. This is to deliver, if you will, desired gases into the vacuum system, okay? So this is really the heart of GEP gas delivery. The four lines out the other side, kind of historically, were kind of more in VPD, but just the skill to make them more fits gas delivery. So that's where gas delivery is a bit more about high purity and, you know, the tight tolerances to deliver accurate gas. This is more about vacuum principles to achieve high vacuum, okay? So they seem, and they are similar, they're kind of cousins, just.
And so there's quality and requirement, the quality
We
requirement.
get quality, typically the quality here is like the smoother surface, right? The ultra hypermetal is more critical here. Here, it's the quality is about, like I said, not creating any bad surfaces, dead holes. You need to be very, there's no machine holes here too, but no, like, I'm touching this. If you then put this in our GA oven, we have so in Hayward, we have an oven that we will pump this down. We will put in things like this. We will pump them down to 10 to the minus, so 10, or 1 to the minus 13 bar, okay? And then we will bake it to 200 degrees C. And then bring it back down to room temperature, and then we do a residual gas analysis scan. And my finger oils would then show up as hydrocarbons stuff. And this wouldn't test. So that's how we know like vacuum products are very clean. So vacuum products also sells into like research, like particle accelerators, like research where they're, the CERN, like, what are they, Hadron Collider. And those have to be super, super pure, but not pure, clean, high vacuum parts. Okay. So it's just kind of related, but a little bit different.
Yeah, delivery and people. We back to product in the Apple. Before and after we make the product. That's why we need to CDB very clean.
Yeah.
And no practical because people the gas into the product. The gas will go back to the product. But no.
Okay? Sure.
Can I go back to that?
Yeah.
The main one related to the chip is this one. This one is to bring the gas to contact with the water. Alright?
Yes.
So the main one is here. The purpose of this one is what?
Purpose of this one is then after the wafer,
After the wafer.
okay? It's to isolate the vacuum when you need to do work on the chamber or something like that. Okay,
So after the wafer, deep vacuum environment.
yes,
For what?
well. Okay, so I have the wafer, okay, it's in vacuum,
Yes.
okay? If after the wafer's atmosphere, I can't maintain vacuum.
Okay, so this one is to maintain the environment.
Right, so this one is like here, so this is vacuum. This is vacuum, and then this stays vacuum all the way out past another set of pumps.
Okay.
Okay, those pumps then inject it out back into the atmosphere. Okay, so everything, because you have to keep vacuum here and you have to keep vacuum flowing this way. Otherwise, any particles or something can stream back up on the wafer and then the chip doesn't work.
Okay, so can I say that this one is to make the environment better.
Yes,
For this one, to the gas into the buffer.
right,
Okay.
right. This one is, so this is to get the wafer down to vacuum. If we couldn't get the wafer to vacuum, we couldn't make computer chip.
Yeah.
Now, once we have very pure environment, nothing else in there, then we want to put the gases that we want in there
Okay.
to get the desired effect. Okay,
That one is to make the environment.
yes, exactly.
For this one.
For this one to work, yeah. So let me just
Good question.
Yes.
Good question.
So in making a wafer, so we talked about there's a deposition, right? There's cleaning, there's etching, okay? There's particle acceleration, okay? And then there is lithography, making the, flashing the light. Those are the six main equipment areas needed to make semiconductor, okay?
But lamin amount is only the 4 and the 5. Can you show slide again, please? The H and the what?
So, well, laminate actually, they're both a little more. Let me go back again.
H, chip,
Yeah,
the 4th and the 5th.
yeah. So the one that's missing on here is, there's the ion acceleration, which particle acceleration, okay, but so Lam, AMAT, Tokyo Electron deposition,
That one too.
okay? ASML mainly, Nikon is the other one. Etch, Lam, AMAT, and Tokyo Electron. Strip, Lam, not really applied too much, Lam and a couple small players, like Matson Technology used to do this. Clean, Lam and AMAT. Deposition, Lam, AMAT, Tokyo Electron. Okay, yeah. And then particle acceleration, AMAT does, and a company called Axcelis does. Okay.
ASML, advanced semiconductor material.
Yes. So they make, so in this process, you will hear something called EUV, extreme UV.
EUV.
And then you'll hear deep UV. And then there was another sub deep UV or something, okay? So, okay, yeah, so this is kind of separate from what kind of just forget now for a second. Remember I talked about you put down, you have it with the photo material, and then you have the mask and you flash light, okay? If you think about it, we're making a pattern that is 8 nanometers wide, okay? Extreme UV wavelength is 12 nanometers wide, okay? Deep UV wavelength is 170 nanometers wide, okay? So up until about 10 years ago, we were making 20 nanometer features with a 170 nanometer wide wavelength. So it's kind of hard to do, right? So we hit a wall where we could get down to 12 by cheating, and there's process ways to do it. But getting below is difficult. So the only company that had enough resources was ASML that developed EUV, extreme UV, okay? And deep UV, which was ASML, Nikon, and Canon, they basically, use a laser, and the laser shines through an optical column, and, they're basically a shutter that flashes so later. EUV is so hard to make, it's actually, there isn't a laser we can make it with. They actually they have a chamber where they're dropping molten tin, and then they're hitting the molten tin with a laser as it's falling, and the molten tin evaporates, and it emits an EUV photon in that process. And that EUV photon is then channeled to it. So it's extremely super technical science. The EUV machine is about the size of this and the next 3 rooms. It costs about $100 million or $150 million per EUV tool.
You go too far already.
Sorry.
Then.
But it's it's super technical.
Yes. Okay, that's
I'll stop for today. Yeah.
things to understand more.
Does this help a little bit?
Yeah, a lot.
I'll try and make it.
70%.
Yeah.
70% understand.
Okay, that's good. Again, I can do that. I just threw this together for the last night and this morning a bit.
I record the teams already.
Yeah.
Watch it later. One.
Okay.
Leave it there.
I'm not sharing. Am I sharing?
Can you? Yeah, we're here. Thank you. In MDC,
Yeah.
in MDC, hope have this kind of knowledge, similar to you, who else?